Now, I explain eigenfunction and eigenvalue. Both the eigenfunction and eigenvalue are defined for an operator h. A function f is an eigenfunction of h, when the obtained function, where h acts on f, equals to the original function f multiplied by a constant value. This constant value a is called eigenvalues. We can express it as a formula like this. These may be new words for you, but in fact, we've already solved a similar problem about wave in our previous video. This equation, which appeared in the wave problem, can be regarded as the problem to find an eigenfunction in which the eigenvalue becomes minus square of omega over v when h is the second differential operator. In addition, the Schrödinger equation we are going to study, also has a structure of eigenvalues and eigenfunctions. In the case of the Schrödinger equation, an eigenfunction is often written as the Greek letter psi, and an eigenvalue is often written as the capital letter E because it represents energy. Let's move on to question 2. The problem is to provide an example of eigenfunctions when h is the second derivative of x. The first example is the exponential a, x. The second derivative gives the square of a, as the eigenvalue. The sine and cosine functions are also possible, because when differentiated twice, both yield minus a squares. An exponential function with imaginary numbers in it, called exponential I, a, x is also applicable. Since the first derivative produces I, a, and the second derivative produces another I, a, and the square of I becomes minus 1, it finally provides minus a square. Note that exponential I, a, x is equal to the cosine ax plus the I sine ax, from the Euler equation. Hence, this function can be regarded as a function like a wave as well as a sine or cosine. Note that exponential a, x, is an exponential function, whereas the sine, cosine, and exponential I, a, x, are functions like periodic waves. The eigenvalue is also positive for exponential a, x, but those for the other three are negative. With these ideas in mind, we would like to reconsider question 4 in the problem of the wave equation explained in the previous video. The problem is to consider a displacement function called xx that satisfies this equation. The operator h is the same as the second derivative we are talking about, but the eigenvalue must be negative because the square of omega over v with a negative sign is always negative. Therefore, exponential a, x, cannot be an xx because of its positive eigenvalue, and only the wave-type functions can satisfy this eigenfunction equation. Keep in mind that the Schrödinger equation has a similar argument. Question 3. The operators h is defined as the sum of the operator hx and h, y. Hx works only on x, and the eigenvalue and eigenfunction of the operator hx is expressed as a, x and fx. Similarly, the eigenvalue and eigenfunction of the operator h, y is a, y and g, y. The problem is to prove that the eigenvalue of the operator h is the sum of a, x and a, y, and the corresponding eigenfunction is the products of fx and g, y. We make h act on the product function fxg, y. There exists two terms, one is that hx acts on fxg, y, and the other is that h, y acts on fxg, y. Consider the first term. The operator hx acts only on x and has no effect on y, therefore, g, y is treated as a constant for hx, which yields a, x fxg, y. Similarly, in the second term, the operator h, y acts only on y, treating fx as a constant, and it yields fx ayg, y. After adding two terms, it is verified that a, x plus a, y is the eigenvalue, and fxg, y is the eigenfunction for h. Please keep in mind that this concept will be very useful when solving multidimensional Schrödinger's equations.